Okay, so good morning. It's very happy to see you guys again today. Last time we have stopped at the half of chapter 7, which is just the standard variation of sampling distribution. And as you can see, although for the sampling distribution of X bar, we cannot directly derive a possible prediction for sampling for the X bar, at least right now. But for the standard deviation of X bar, which we know here as sigma X bar, we can somehow derive it according to the population standard deviation. And today, I'm gonna telling you the most important theorem in statistics, which is the central limit theorem. I used to say that if there is a kingdom of statistics, then the central limit theorem should be the crown of that whole kingdom. It means the power, it means all the authority of statistics. So briefly say, the central limit theorem is talking about the distribution of X bar. So in the last class, we don't know whether the X bar will distribute in some way. The only thing we know is by expectation, eventually if you trying to do the sampling repeatedly for enough times, you can get an expectation of X bar, which is exactly equals to the mu, which is the true value, and as well as the population mean. So although in the textbook we give you that equation by default, but I would also let you briefly know there is actually a theorem behind it. It's the so-called law of large number. Well, I mean, the derivation of law of large number is not in our contents. So now, as long as we have made sure the expectation of X bar will eventually approximate to the true value, then our problem becomes, how could we get the expectation of X bar? Right. So here is the place of central limit theorem. So central limit theorem says, no matter your population distribution is, your population can be can follows a uniform distribution. It can follow some others like exponential distribution, is not even symmetric. It's all okay. No matter your population distribution is, once your sample size is large enough, the sampling distribution of X bar can be approximated by a normal distribution. So that's the content of central limit theorem. All right. So well, the following in the first sentence inside this slide, you can see. So it's quite intuitive. When the population follows a normal distribution, we will say, okay, it's quite natural to expect that the sampling distribution of X bar will also follow a normal distribution, no matter your sample size is large or small. All right. And then after this intuitive understanding, the most valuable part of central limit theorem is here is even though your population distribution may not be a normal distribution, it can take a variety of shape. But eventually, once your sample size, we set a threshold here, once your sample size is larger than 30, then we could see that the sampling distribution of X bar will somehow get close to the normal distribution. That really brings a lot of benefits for our analysis. So if you think about that, no matter the population variance or the population distribution is, we don't really need to care about it in our analysis. But in our analysis, we can always make our analysis according to the approximate sampling distribution of X bar, which is a normal distribution. That simplifies our analysis a lot, right? So, but how this central limit theorem to be true? So here you can see a record of experiments. So in this picture, in the first row, there is 3 different populations. You can see the first population follow a very typical uniform distribution. And the second one is just like a reverse version of normal distribution. It takes the least possibility, it takes the smallest probability density in the mean in the mean value, but getting much higher, the probability density getting much higher on both ends. Okay, then the third one always becomes more strange, right? So it is exponential. So these 3 distributions are really different from each other. Then what we did is in the second row, we try to record the sampling distribution of X bar when we limit the sample size n equals to 2. So we do the sampling for all possible cases. Okay, so if the population 1, say it maybe have say 100 observations, then we really did a C 102, which means we pick up 2 observations from 100 observations without considering another result. Okay, so that's the combination rule we have introduced in before. So we take all the cases, we take all the possible cases for n equals to 2. Then you can see, look, for the uniform distribution of, okay, so for the population following uniform distribution, we actually see the sample distribution of X bar are likely to center at their mean value and as well as the median. Okay, so it turns from rectangular to a triangle shape, like this right now. So for the reverse normal distribution, the second column here, you also saw some similar pattern. Even though for the original population distribution, it would take the least probability density at the center, but now it seems like in the center, it takes the highest probability density for sampling distribution. So you can see, although we take our sampling distribution, we take our sample from the population, but by the end, the sampling distribution of X bar may not follow the population distribution accordingly. Right. And to make our analysis more precisely, okay, we do increase the sample size. So which is the record in third row. Okay, so in the third row, you can see it gets much closer to a normal distribution for all the 3 different populations. Okay, and then if you transpose n equal to 30, even for the third column, which corresponding a very right field, the exponential distribution, nothing related to the symmetric feature in the original population distribution, but you can still see that the sampling distribution of X bar, once you increase your sample size to 30, it very looks like a normal distribution. Okay, so the central limit theorem is a theoretical conclusion for this feature. All right, so it's just a record our practice here, and it becomes a series. So once a practical record becomes a series, then it means that even though you don't do those sampling distribution in your work, you can still try to follow the theorem. Okay, so later you will see that I never do a sampling process for the remaining chapter, for the remaining part of chapter 7, but still we can utilize the central limit theorem. So that's some difference between the so-called theoretical framework and our practice. All right. So take it easily. Okay, the central limit theorem we talked about. If you select a random sample of n, of size n from a population, then the sample distribution of the sample mean x bar can be approximated by a normal distribution as the sample size becomes large enough. So that's the definition of central limit theorem. And please note that the process is the so-called approximation. So in practice, yes, we do see that in the picture here, the sample distribution gets very close to normal distribution, but still, this sample distribution is getting from a finite repetition of sampling, right? So we draw this distribution by using a limit number of experiments, right? So, you know, the normal distribution by right, it should be a continuous random variable. It should be a continuous distribution. And here we are using some discrete outcomes to approximate, to approach the sampling, the normal distribution. And that means if you try to draw a conclusion that the sampling distribution is the normal distribution, is exactly the normal distribution, that's totally wrong. We are trying to use finite number to approach some infinite number. Okay, so that's the meaning behind approximation. Then here let's use a real world example to describe the central limit theorem. We still use the AI boundary example, with it's all the same for all these examples in chapter 7. So with the previous learning, we will see that once we know some true value, the first is the expectation of x bar. It is equal to the mu. In this AI case, is 51,800. That's it. We can also have the sigma of population, which is 4,000. These two values, we call it truth, right? It is some truth, or formally say we call it parameters in the population. With these two truths, so first, with the variance, with the standard deviation of the population, we can first derive the standard deviation of sampling distribution of x bar according to our previous learning, right? So because In our case, our sample is only 30 observations, and total population is over 2,000. It's around 2,500. Okay, so it's quite reasonable for us to believe that the sample is approximate to the so-called infinite population. So the criteria we have talked about before, so it's like n over the uppercase n. So the sample size over population size, once it's smaller than 5%, we say we can ignore the finite population correction factor. We can somehow assume that the result for any calculation here is approximately close to some calculation under infinite population. Then once we try to calculate the standard deviation of x bar, we can directly use the sigma, which is the population standard deviation divided by square root of n. Here is 4,000 divided by square root of 30. We get around 700. Okay, so what we have done here is using some tools, using some parameters to calculate some very important feature of our sampling distribution. And that's not the end. That's actually not the end, right? So you all just learned the central limit theorem, right? With the central limit theorem, if we want to have a very complete description of the approximated normal distribution for the sampling distribution, we need two factors. We need to say parameters, but this parameter is not the population parameter, it's a function parameters. Okay, so we need two function parameters. One is the expectation of x bar. The other one is the standard deviation of x. Right. So combining these two, we can define a normal distribution regarding x bar. Okay, and we have the normal distribution here because of the central limit theorem. We just use the abbreviation CLT here. Okay, so because of the CLT, now we don't only have these two boring numbers, but with these two numbers, we can construct a very specified distribution for the sampling distribution. Okay. Then with this distribution, it's a well-defined one. You know the mean value, you know the variance. Then according to the shape, according to those statistical table of normal distribution, we can draw the graph according to the function parameters here, and we can get the probability density function for any point located in this distribution. Right. So, well, in this distribution, we cannot just know x1 here because now in the center is not an expectation of x bar, it is an expectation of x bar, since we are talking about the sampling distribution, but not a distribution for a random sample. Okay, so in other words, we are talking about the distribution of a lot of samples, of the mean value from different samples. Okay, so we are not talking about only one sample, but we are talking about the tremendous plenty of different samples we can get, but we just use the mean value from each sample as a representative. So the mean value here is the expectation of x bar. The parameter, the function parameter that define the shape of this function is a sigma x bar. Okay, we have this value. So for any point in this distribution, we say that's our x bar 1. Okay, we won't really say that this x bar 1 is our say first sampling. We don't really necessarily need that. Okay, this is just the sum one of our sample mean. Okay, so for this sample mean, no matter what it is, you can find a corresponding probability density function value for it. Right. And once we have found the value for any probability density function, one outcome we can have is we can get the size of any area we define. Right. Like if we try to define an area that is symmetric around the mean value, somehow like this. So okay, so this is x1, this might be x bar. We just say the area here is symmetric. Okay, it takes 50% of it on the left-hand side of expectation value, and also have another 50% of area on the right-hand side of the mean value. For this area, with the corresponding probability density function, with two clear values for x bar 1 and x bar 2, we can get the size of this area, right? We can get the probability because for continuous random variable, the area is the probability. Once we can get the size of this area, we can get the probability that your one value can fall in this range. Okay, so that's about normal distribution. And considering about our current context, we are talking about the sampling distribution. Right, the sampling distribution is talks about all possible x bar, all possible sample mean, right? So considering about our previous learning on normal distribution and our current learning about sampling distribution, we may say that once if we define a specific range around the mean value, we can define the probability that, which is the side of the area, the probability that an x bar will fall into this range. So okay, let's make it as simple as we can. So what we are talking about here is we are trying to make some prediction. So in this distribution, we use the population mean, we use the population standard deviation as the sum as a representation of sigma x bar. So we use the true value, we form a theoretical framework without doing any actual sample. Okay, so in this sample, we don't do any real world sample yet, but we just construct the ideal thing. And with this ideal model, with this ideal distribution, we can somehow predict the possibility that once if we do one sampling later, the mean of that sample will to some probability that fall into a specific range we define. Okay, so take it with some numbers. Okay, so once if our say the average number here is 51800. Okay, so that is our following example. We say we want to have a range plus minus 500. So the lower bound of this range will be 51300. The upper bound of this range will be 52300. So we define a range plus minus 500 around the mean value. Okay. We want to predict that if we do an actual sampling after we constructed this theoretical framework, could we predict that with which probability the X bar, the sample mean, will fall into the defined range? So that is a key problem, a key question we want to answer in chapter 7. And the process to solve this problem is just like the process we trying to get the probability in a normal distribution. So there is not much new things, but just use the thing we have learned in chapter 6 about the probability with normal distribution. And now we just use some different context, use some different notation. Okay, so before we talk about some normal distribution for a random X. Okay, now we are not only talk about X, but we are talking about a specific context, which is the sample mean. We are in this distribution, we are talking the sampling distribution, which is the distribution of all possible sample mean if we do the sampling. All right. So the way to solve this problem is quite easy, actually. So just ignore our slides right now. So our slides show you how to use your hand to calculate the probability. Let's just use a very intuitive way. So in this question, if you have Excel, if you have a laptop on your hand, you can calculate the probability here easily, right? To calculate a probability inside for this area in the middle, you should utilize the cumulative density distribution function, right? Which is, if we use the norm dot this function represents the normal distribution in Excel. We use this function. We have 4 inputs, right? The first input is the X. For this case, we first use the upper bound. Okay, we use 52300 first. Then our second entry is 51800. All right. Third entry, sigma X bar we have calculated here is 730.3. And we use 2 to represent cumulative distribution function. So what I have done here is I'm trying to calculate the size of this area. So start from negative infinity to the upper bound, which is 52300. This function, as we taught before, calculates the size of this area. And to have the area in the middle, we need to take out something we don't need. We need to take out the area on the left-hand side of our lower bound. So we have, if we define the first one is P1, so it's about probability, okay? Then our P2 is still we use a normal distribution. But here, our first entry should be 51300, which is our lower bound. And Other things are the same. Okay, same mu, same sigma, same true or false definition. So what this P2 define is about the remaining left tail here. Okay, so it is about the area for this left tail. Then, okay, the last step, we take the difference of P1 and P2. Then we get the size here. In this case, the size should be around 50%. So let me describe what we have done here, okay? Let me describe it again. So what we are trying to do here is we use some parameters from the population to construct the theoretical distribution of the sample mean. With this theoretical distribution, even though we didn't do any sampling yet, even though we don't have any real value for X bar, we can do prediction for our subsequent actions. We use the area inside normal distribution, which represent the probability. We use this probability to predict that to which possibility, how possible that an actual X bar will fall into the corresponding range we define here. So that's the process. Okay, eventually, with this number, which is around 50% probability, the conclusion of our analysis is with the probability. Okay, let me just formally say conclusion here. Okay, with probability equals to 0.5034, and X bar would fall in the range in between 51300 to 52300. So yeah, then maybe some of you may have a question that, so what's the point for us to have such a analysis? Okay, so I mean, yeah, we know there's more distribution, yeah, and we know there is some new thing called central limit theorem. But why? Why you want to combine these two? Why you want to get this prediction? So what is your contribution here? To me, I would say the contribution here is before we have done this analysis, even though we observe any truth, even though we observe any population parameter like this, we observe two very valuable, very precious parameters from the population. That's very rare, right? I have said usually for the population, we don't really know what exactly the parameters are. Okay, but now, yeah, we somehow get some very precious data, population parameters. Before we do such an analysis, before we utilize the central limit theorem, we can only conclude that, okay, yeah, there is one parameters, there is one another parameters. That's all. We have nothing to say about the sample, about the population. We can just say what we have observed. Okay. But right now, with the central limit theory, with some knowledge of normal distribution, we do something more, right? Even though we don't do any sampling. Okay, so by the time, let me emphasize this again, by the time we do such analysis, we never have any one sample on our hand. So all of them are impaired. All of them are like some pure theory. Okay, also we do some calculations. Okay. All of them here are really pure theory. But with those pure theory, we can have some guidance for our subsequent practice. So that's a value. That's a value here. With these two truths, with these two population parameters, we can predict that if we do a sampling, if we try to make up a sample, then the sample mean should fall in the range, in a specific range we define with a specific probability we can calculate. So this process, this analysis is a very key part. It's the only key part of Chapter 7. And I would like you to remember this, to practice this in your homework, in the lab assignment test. Okay? Okay, let's come back to the slides. Okay, so in the subsequent slide, here we have one page on use of Excel to compute the sampling distribution of X bar. So here I exactly write down the process we have used here using the Excel function. Okay, but in the previous slide here, the two slides before that Excel functions, we have something can be done with our hand and as well as in your exam. So in your exam, the only statistical table you can refer is the standard normal distribution one. Right? We cannot have infinite numbers or infinite tables for different normal distributions. Right? So we can only say try to use only one standard normal distribution table to fit all different questions with all different normal distributions, since we can always standardize some values in a specific normal distribution to the standard normal distribution, right? So the process with hand is nothing much different from the one with Excel. The only additional thing is we need to do the standardization. We need to calculate the z-score for upper bound and the lower bound. For the upper bound, we have 52300. We have the z-score here. Let me know the notation here. Z for upper bound. Z sub upper bound. This is 52300. You should first minus the mu 5100 divided by not the population standard deviation. Because now you are talking about the sampling distribution, you need to use the standard deviation of the sampling distribution, which is the sigma x bar 730.3. You get this over. So 68. Then after you do the standardization, you can utilize the statistical table to calculate the possibility that any z value smaller than your upper bound criteria, z smaller than z sub upper bound. This is z smaller than 0.68 by checking the table for normal distribution, for standard normal distribution, sorry, you get a probability. Okay. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. 0.7517. here, the first probability we get here is exactly the same thing we got here, the P1 here. We still calculate the size of this area on the left-hand side of upper bound. And our next step is the same as we have done here. We need to calculate the P2. We need to have the z value for the lower bound, which is you actually don't even need to do the calculation here. Once you notice the feature of standard normal distribution, the feature of standard normal distribution, one important feature is the mean value of a standard normal distribution is 0. So if we define a range, a data range which is symmetric around the mean value, that means if we have an upper bound which is 0.68, correspondingly the symmetric lower bound should be the opposite value, negative 0.38. You don't even need to do the calculation. Once you make sure that your lower bound and upper bound are symmetric around the mean value, you just say, okay, here is negative 0.68. And exactly, this is the value. And calculate the p-value for z smaller than negative 0.68. Well, for this one, you can, for this probability calculation, you cannot apply the same subject easily by using a symmetric field. You still need to check the statistical table. Here you will get the value of 0.2483. Take the difference, P1 minus P2. So this first one is the P1. This is the P2. We have exactly replicated the process here by using our hand, by utilizing the statistical table for standard normal distribution. So because we are trying to use our hand to mimic the Excel function to some extent, okay? So we need to spend a bit more effort, but eventually we will get the same result, which is 0.5034. That's the probability that a subsequent sample mean, if we do our sampling process, that for that sample mean, there is a probability equal to 0.5038 that X bar will fall into this range according to the lower bound and upper bound. So, right, to conclude, you see this cause death and this cause death. We are actually doing the same procedure twice. One is using Excel, the other one is using our hand, and it's a statistical table. All right. After that, let's talk about a small point, which is the relationship between the sample size and sample distribution. So in this calculations, although here it seems like don't have anything related to the sample size, but before we calculate the probability here, I would like you to notice that we actually used the sample size when we try to calculate the sampling distribution. When we try to calculate specifically the standard deviation of sampling distribution, the sigma x bar here. we need to use the population standard deviation 2 divided by square root of sample size to have our eventual sigma x bar. And from the formula here, you can easily understand that this formula reflects our information fetching process. Okay, once you increase your sample size, the variance or standard deviation of your sigma x bar of your sampling distribution, it goes up, right? You're getting higher sample size, larger sample size, you're getting lower sigma x bar, smaller sigma x bar, okay? That means if you draw the corresponding normal distribution for a large sample size and a smaller sample size under the same population, okay? For a larger sample size, because the sigma x bar turns to smaller, you should get a normal distribution for the approximated or normal distribution for the sampling distribution narrow. Right. Then for this one is large. And if n is large, sigma x bar is small. For n is small, your normal distribution for the sampling distribution should be flat. So that's the difference. And with different distribution, if you lower down the standard deviation of your x bar, you use the same value here, like if you use it in a normal distribution function, you're very likely to see once you have a smaller sigma x bar, you should have a much higher P1, much lower P2. Eventually, the difference between P1 and P2, it increases. So in conclusion, that means if you increase your sample size, you will decrease your sigma x bar, and eventually you will increase the possibility that x would follow in the range you define. So, in other words, increase your sample size improves the precision of your prediction. It improves the accuracy. That's the key point I want to tell you in this class. So to conclude is, once you increase the sample size, the sampling distribution with a larger sample size has a smaller standard error, then the values of x bar, the possible values of x bar, have less variability and tend to be closer to the population parameter, the population mean. That makes your prediction more accurate. So from this picture, you can see once you increase your sample size, the distribution becomes narrow like this. Okay, so the previous one, the previous distribution is like this one quite close to the normal distribution, but now you get much narrower one. You can increase your accuracy in your prediction. Okay. All right, we have 25 more minutes that are about the sampling distribution of P bar. So P bar reflects the sample proportion. We have defined P bar newly just in this kind. Okay, in the previous factor, we don't really have the P bar thing. Okay, but it's not really hard for you to understand. So actually, if you think about our typical example for picking balls from a box, okay, for calculating X bar sample mean, we just picking balls, these numbers, like they say in this first ball, okay, we have say 5 balls in this ball. Maybe the first number is 1, the second number is 7, the third number maybe like 6, maybe then 8 or 3, something like that. Okay, then the sample mean should be 1 plus 7 plus 6 plus 8 plus 3 over 5. Okay, that's just an example. You can freely select your preferred number in the example. Okay. So that's a very common example, very generalized example for X bar. For P bar, the question actually got much simplified because for P bar you only consider two things. So you only have two types of balls. One is from yes, the other is from no. So to link our knowledge with some previous learning, let's say it's not yes or no, but circumstance and the field. Still we have 5 balls, but we have 3 circumstances who fail. Then the P bar here is 3. Say we say the P bar is a proportion of success. That is 3 over 5. This looks like something similar to our previous learning outcome, right? It looks very similar to the binomial procedure. P bar here is the P, the possibility in binomial procedure that indicate the possibility of success in 1/12. Right. So, despite we have the same similar law of log number for P bar, which indicate that the expectation of P bar should also equals to the population proportion, which makes sure that our analysis is useful. Comes to the standard deviation of P bar, which we can also call it the standard error of the proportion. You can see there is something very nostalgic for us. For infinite population, the sigma P bar is the square root. If we just split the numerator and denominator, it is the square root of P multiplied 1 minus P over the square root of sample size. So the numerator here, if you recall our conclusions for the binomial procedure, the variance of x is P multiplied 1 minus P. So, in other words, the population standard deviation for proportion analysis, it is exactly the standard deviation for a 1/12 binomial procedure. You see, for binomial procedure, the variance should be n multiplied p multiplied 1 minus p, right? If you just take n equals to 1 and take the square root of the variance, you get the standard deviation here. So that means when we consider about the population here, we are like trying to do only one round of peak from this box. Okay, since this box have 5 different balls, 3S, 2F, the probability for us to pick up one ball which is success is P bar here, 3 over 5 here. The process here is exactly like a 1/12 experiment of binomial procedure that with a P, a probability of success equal to 0.6. All right. So yeah, and come back to our last slide here, because P bar is just a simplified version of X bar. Your X bar is calculating the mean of various different numbers. P bar is like calculating the average of 1 and 0. Okay, if 1 represents X and F represent 0 represent fail. Okay, then your P bar is just calculating the average of a lot of X and a lot of 1 and a lot of 0. Okay, so these two are basically identical thing, just for different population. So you have law of large number for X bar, you also have law of large number for P bar, which can make sure that yeah, our sample is useful. Any effort we have done here to collect a sample is some right effort towards the truth. And when you're trying to describe the standard error, you will have something very looks like a 1/12 single trail binomial procedure. And one thing I need to mention is there is still a limitation for central limited theorem to apply into sample proportion. Okay, so for X bar, we have normally, so common, let's don't use normally because we really have too much normal in our context. Okay, let's say commonly, we need to have a larger or no less than 30 to make sure that your sampling distribution can be approximated by normal distribution. Okay, for some very highly skewed one, you need to have a much higher criteria, which is n over 50. And sometimes for some symmetric one, let's go back to the slide here about central limit theorem. So for some more symmetric distribution, you can have n just over 15 is enough for you to apply central limit theorem. Okay. For proportion, I have said here, proportion is just a simplified version of X bar. Okay. No matter you consider about the P bar proportion, symbolic proportion itself, but also when you consider about the expectation and the standard error, they are exactly similar to the expectation of X bar and the single X bar. Okay, and you can also have something like n over 30 as a criteria for you to apply central limit theorem to P bar to the sample proportion. Okay, but then here is some problem. If you only say n larger than 30, you will have one problem, which is once we have some extreme case about the population proportion, say here we have a 3 versus 2 for population of 5. Okay, then if we have a population, we say big uppercase n equals 100, but we only have and fail. So it's like only 10% of it is fail. So if you define a P population proportion which is proportion of success, P should be equal to 0.9. All right. But once you pick only 30 observations, you may find that, okay, you are very likely to pick up 30 all success balls from 100 balls, if the 100 balls have only 10 fail. But it's very possible, right? Because there's really too many success balls. If you only pick up 30 from the 100, you are very likely to pick up all success without any one fail. Then, if you calculate your proportion based on your sample with all success, your proportion will be easily 1, and it's much less. So in some extreme case, that may affect your analysis. Okay, so considering about the proportion, we revise our criteria for approaching. We revise our criteria for central limit theory. We require that n multiply p larger than 5 and n multiplied by 1 minus p also larger than 5. So that makes sure in your population there are enough number of failure, enough number of success, or enough number of fail corresponding to your sample size. So when you're trying to do a sampling, you are having enough probability to pick up both success and fail. So that's the meaning of this requirement. Okay. So we can also have some calculation, for example, for the sample proportion. Still, we use EAI case. Okay. So here is an EAI case. We know that some full value, we know the population parameter regarding to proportion, which is the proportion of employees who participate in the management training program. In the population, we have our parameter P equal to 0.6. According to this P, if we make sure that we meet the criteria here, that asking us to give enough probability for the sample to pick both success and fail, then could we also apply the central limit theory to the sampling proportion and try to do the prediction we have done here? That's viable. In this case, say we still use the sample size n equals to 30, right? And we try to define a range around. The expectation value is plus minus 0.05. So to write down an interval, this range is 0.55 to 0.65. So the question becomes, to which probability, how possible that if we observe a sample and we observe the corresponding p-bar, how possible that p-bar will form into this range? So to solve this problem, first we need to have some validation. Okay, we need to validate that. So NP here, 30 multiplied 0.6. Okay, we have 18, which is larger than 5. We have and minus b, we have 30 multiplied 0.4, which is 12, still larger than 5. This 2 makes us. So this is because this is so CLP, the central limit theorem, is applicable. Then, before we calculate those probability and usual things, what should we do? We need to have the standard error, right? Which is the key, which is the key parameter that describes the table, right? And one benefit you can see, you don't need to have something called population variance because this one proportion represents some mean value, but also indicates the variance. Right? Sigma p bar, let's use the p. Square root of p multiplied 1 minus p and divided by the square root of n. You eventually get 0.0894. You don't really need a population variance, right? So following this procedure, let's just use our calculation with this score. Okay, so that because that's much more closer to your exam. Okay. So still we need to have a z-score for upper bound. Your upper bound is 0.65 minus the average. This one is the population mean. Okay, divided by the standard average just calculated. 0.0894, you get 0.56. Okay. Correspondingly, you get the probability for NZ smaller than this criteria you are working on. Calculate the size of this area. Okay. On the left-hand side of upper bound, which is 0.7123. And some simplification you can use for lower bound is because this for centered at 0 for lower bound because you are defining a range which is symmetric around the mean value. This should be minus, okay, negative 0.56. Okay, for the lower bound, you have z smaller than negative 0.56. You have 0.2877. This one is P2, this one is P1. Eventually, probability is P1 minus P2. Writing down its equation is P minus 0.56 smaller than Z smaller than positive. So Z4 into this plus minus 0.56 range. Probability is just the difference of probability 0.4246. Okay, so for the proportion, we just do the same calculation, almost the same calculation as we have done with X bar. All right. So that's all the everything I want you to have for this class. And this is very important, I would say, for not only our current campus, not only for our upcoming exam, but also it is the only foundation for the interval estimation for the hypothesis testing. So please make sure that you understand every step, you can understand origin, motivation, and the eventual conclusion I have listed here, you will understand the contribution for this analysis. All right. Okay. One more important thing I want to mention is, so until now, I'm actually very silent about why we define a range which is symmetric around the mean value here. So maybe anyone give me some guess, maybe some possible explanation and why I select the range here, but not some random range. Like, I mean, to get any range in between two values, in between one lower bound and the upper bound, we can use the statistical table or the normal distribution function in Excel to do the calculation, right? We don't really need to restrict our analysis inside into this range. But why? For all the example here, I use a range around the normal around the mean value. Okay, so yeah. All right, okay, good, yeah, very close actually. So what you are talking is like here it looks much approachable. Okay, so let me conclude it informally. So we define a range, a symmetric range around the mean value because the feature of probability density function for normal distribution. We know that for normal distribution, the mean value is not only the mean value, but also the median and the mode of the distribution. So that means although the probability density function cannot represent the probability itself, but intuitively you can see inside this distribution, the mean value is the most possible value that for this random distribution X bar can take. Okay, this is the most possible value, the expectation. So once we want to make a prediction, we want to make our prediction as inclusive as we can, as much precise as we can. Okay, then the largest probability for a fixed range. Okay, so here, like for the X bar example, our range is plus minus 500. So totally the range is 1,000. For a fixed 1,000 range, the largest probability we can get is with a range symmetrically around the mean value, right? If we define this 1,000 range like in the very end of the left tail on somewhere, then the probability you get for this range on the very end should be very close to 0. Then what is the point for you to do the analysis? So that's one thing, that's one important part I want you to know. And why we start our analysis around the mean value? Why we try to stick to the expectation of sample mean? Why we want to stick to the population parameter? Because we can optimize our prediction by utilize the feature of normal distribution. Okay, so this is all of today's class. I'm trying to be slow, trying to explain every single point clearly. I hope you can go back to review at least one example here. No matter you use Excel or you use the Z-score by hand, at least I would like you to make sure that you understand the motivation, the calculation, and the contribution of all the analysis here. And you will see that for chapter 8, if you understand this process in chapter 7, you will have a very easy travel in chapter 8, because chapter 8 is just a slightly twist of current analysis. Okay, so that's all. And if you have any questions, just come to my office by my office hour. And that's all. See you next class.